Today and in the subsequent lectures, we will be talking about dimension reduction techniques in multivariate analysis. As you know, dimension reduction is necessary when there are a large number of variables and we want to reduce the number of variables, so that it is easier to comprehend the analysis and to make interpretations simpler. Now, there are several dimension reduction techniques like principal component methods, factor analysis methods, canonical correlations and multidimensional scaling. We will look at them one by one. Today we will start with the principal component methods, and in this lecture we will be looking at what principal component analysis is really all about. We will be illustrating that with a few examples as well, and in the subsequent lectures we will be discussing in detail the principal component analysis. Let us begin by looking at what dimension reduction really means. It means that we ask the question whether it is necessary to look at all the variables, or is it possible for a smaller set of variables to capture the same information. This happens when you have a very large set of variables, and then we would not like to work with too many variables because it makes the study cumbrous, and the other thing is that interpretations become very difficult. So, you want to select a smaller set of variables. We can do this through several techniques. The most important of this is the principal component analysis, which is the most popular also, the factor analysis, which is widely used in psychometry studies, the canonical correlations and the multidimensional scaling. What we will be looking at in this particular module would be the principal component analysis. Now, the principal component analysis helps us to capture the variability of a set of variables through a few linear combinations of the variables, and these linear combination of the variables contain most of the information that is contained in the original set. So, what we do is basically we reduce the original number of variables to smaller number of variables, which are primarily linear combinations of the original ones, and moreover they contain the same information. So, one help that it does is that it reduces the data, in the sense that you have lesser number of variables. If you have a particularly if you have a very long list of variables, this is very helpful. The other is that the interpretation becomes easier, because if you have fewer variables, it is easier to capture the underlying mechanism of the model, and once you do that, it makes it much easier to interpret the results that you get. So, these are reasons why we actually do principal component analysis. Let us have a look at an example. In this example, this is a very traditional example. So, we have in this case several individuals whose heights and weights have been measured. On the x axis, we have heights minus 160. So, these are in centimeters. So, we have actually shifted the origin, and the weights are taken as weights minus 55 kilograms. So, once that is done, we have a plot of the heights and the weights. Now, if you look at this, what we want to do basically, this is a very simple example. So, we have two variables. The question is, can we reduce it to a single variable? And the answer is yes, if you are using principal component techniques. We will go through the techniques later on, but just see how we can do it. Suppose we rotate the axis. The original axis was along heights and weights. Now, the new axis are the red ones, one going right across and the other is perpendicular to this. Now, what it really means is that we have rotated the axis to certain degrees. We will see later that we will call this an orthogonal transformation of the original variables. And now, look at the variables. You see, if you look at the red lines, the principal line that is going right across, that one contains most of the x very near it. So, it is widely dispersed over the red line, and over the second red line, which is perpendicular to it, the variability is not that much. So, you see, in the original data, heights and weights are very widely distributed. So, the variability was high. In this case, if you take the longer line, most of the observations lie along this, and hence the variability along this line is high, whereas the variability along the perpendicular line is much smaller. So, what we do is, if instead of the two variables heights and weights, we take just the combinations. Mind you, this red lines are combinations. So, the first red line is say y 1, which is a11 x 1 plus a12 x 2, and the second red line is y 2, which is a21 x 1 plus a22 x 2, these two lines being perpendicular to each other. Now, if we just take y 1, you can see that all the variability almost lies on y 1. So, we will discard y 2 and work with y 1. So, instead of two variables, now we can look at only y 1, which accounts for the maximum variability, so that we do not lose much information if we drop y 2, and we have made a reduction in the number of variables. Now, this is a very simple example. In fact, two variables are not too many. So, very often we will be working with two variables, but you can see from this technique that we can actually reduce the number of variables, whether it be it from 2 to 1, or maybe from 100 to 5 or 6, or maybe 1000 variables to 10 or 15 variables by the same technique, as long as they account for the more or less a high percentage of the variability in the original data. So, this is primarily what principal components will do. Now, let us look at the general model for principal components. So, we have m variables x 1, x 2, x m. These are the original variables, and m may be very large. So, the number of variables may be large. What we do is, we take a linear combination of this x 1, x 2, x m and form y 1. So, a 1 1, a 1 2, a 1 m are the coefficients, and we write y 1 as the vector a 1, which consists of a 1 1, a 1 2, a 1 m, vector a 1 prime, the x vector. So, this is one transformation. We can have another transformation, y 2 is equal to a 2 1 x 1 plus a 2 m x m, etc., or in general a 2 prime x. And similarly, given x having m variables, we can have similarly m variables for y, which are y 1, y 2, y m. In short, we will write this as the y vector is equal to the coefficient matrix A into the x vector. The coefficient matrix A is composed of aij's, of course. In this case, y 1, y 2, y m are referred to as the principal components, and y j is the jth principal component. Of course, we have not still chosen the principal components properly. That will depend on how we choose the coefficients A. So, if a proper selection of that is made, then we will end up with the principal components. So, the A's at this stage are unknown. The question is, what is A? Once A is defined, the whole model is known to us. Okay? We have the principal components is that. So, that the choice of a 1, a 2, a m now becomes important. Firstly, what we need is, we need a 1, a 2, a m to be orthogonal. What does it mean? It means that a j prime into a k should be equal to 0. That means, any two of these vectors, taking the inner product of these two vectors, would give us 0. That is one condition that we need. Another condition that we often impose is the condition of normality. Okay? So, basically these are not orthogonal, it is something more, it is orthonormal. Orthonormal means that a j prime a j must be equal to 1, that is the inner product must be equal to 1, or we can say that the length is equal to 1. So, all of these a 1, a 2, a m should be such that they have unit length and they are orthogonal to each other. This is the first condition that we need. The second condition that we will impose is that a 1 is, this is the first variable that we choose, y 1. So, a 1 is chosen such that variance of y 1 is maximized with respect to a 1. So, variance a 1 prime x is maximum such that a 1 prime a 1 is equal to 1. That is the first thing. So, maximize the variance to choose a 1. Once a 1 is chosen, that is, we get y 1, which is the first principal component. we next choose A2. How do you choose A2? You choose A2 as again maximizing the variance of y2, which is A2 prime x, subject to two conditions now. One is that A2 prime A2 must be equal to 1, and the other condition is that A2 prime A1 must be equal to 0. So, A2 must be orthogonal to A1. So, basically this is a maximization under restraint is A2 prime A1 must be equal to 0. So, this way we can go on choosing the AJs. Okay. So, at the jth stage we choose AJ in such a fashion that variance of AJ Yj is maximum, subject to the condition that Aj prime with Ak, where k is anything less than j, are all equal to 0. So, this is how A's are chosen, and we will see how we actually do this in a later class. One important result, again something we will be proving later on, is that the total variability of x1, x2, xm translates to the total variability of y1, y2, ym, which means that variance of xj's summed over j is equal to the variance of yj's summed over j. So, you can see that if you move from x to y, you still retain the same variability. This is obvious because we are making just a orthogonal transformation. But now remember that variance of y1 is the largest of the variances. So, we have the yj's ordered according to the variances. So, variance of yj is greater than variance of y1 is greater than variance of y2, which is greater than variance of y3, and so on and so forth. And moreover, unlike the covariances between xj and xk, the covariance between yj and yk are equal to 0, because the coefficients aj's are orthogonal among themselves. So, this makes the variables yj uncorrelated with each other. So, the two advantages are the covariances between the different principal components are 0, and the variances are ordered in the sense that the first principal component has the maximum variance, the next one has the second maximum variance, and so on and so forth, whereas the last one has the minimum variance. Now, how does this help us? What we do here is that we first take say q of the m y's. So, we will look at y1, y2, yq, and we find out the percentage of the total variability explained by y1, y2, yq. So, this proportion we can find out always, and we can see that if this is large, then we will consider the q variables only. Why? Because you see y1 would capture the maximum variability. So, suppose it captures 40% of the variability, then y2 would capture slightly less, maybe 30% of the variability, and then y3 captures say 20% of the variability. Then together they capture 90% of the variability, and the remaining principal components have only 10% of the variability. So, if we discard the remaining variables and just look at the first three principal components, we would be able to capture 90% of the variability by discarding some of the other principal components. If you want to do better, if you want to go to the 95% level, you can include maybe y4. That is a choice that we can make, and it is basically optimization in the sense that you let go of, you reduce the number of variables and forego a little of the information in the sense of discarding some variability in the process or some information in the process. But very often there is a lot of gain by reducing the number of variables while discarding a little bit of information to do that. Now, let us look at an example. Okay. In this example, we have 5 types of food ingredients. Okay. These food ingredients are actually included in a number of these 12 cereals, and you can look at these cereals composed of the different proteins, carbohydrates, fats, calories, and vitamins, and you will see that the combinations are quite different. So, the problem is, should we be looking at all these 5 different factors like proteins, carbohydrate, fats, calories or vitamins to explain any one of the cereals, or can we reduce it to a lesser number of variables? So, what we do is we do a principal component in this case. Mind you, in this case m is equal to 5, and once we have done the principal component, here is what the results tell us. We find that the first principal component has a variability of 31.82, the second one a variability of 16.17, the third 2.43, and so on and so forth. So, the proportion of variability explained by the first principal component is 79%, and the proportion of variability explained by the second principal component is 20%. The third, fourth, fifth has very little, in fact negligible variability explained by it. In fact, the zeros are very small numbers. The first 2 decimal comes out to be 0, which is shown here. And so, you can see that the cumulative proportion for by the first 2 we explain 99% of the variability. So, what we do is we only retain the first and the second principal component. We can get all the 5 principal components, but looking at them would be a waste of time, because we are going back to 5 variables again. So, we drop the last 3, and by dropping the last 3, what we lose is we lose only 1% of the variability. And you can look at the first 2 principal components given by the first 2 columns here, component 1 and component 2. So, you can see that we have the 2 columns where we have the first component and the second component and the corresponding coefficients, and diagrammatically we can show that these are variables corresponding, or the percentage of the variables explained by the different components. And then what we see is that if you look at the first 2 components, we show that y1 is 0.228 calories plus 0.972 vitamins. You see, the first column has only 2 non-zero values. So, these are the 2 variables that come up, and these are the coefficients, and we saw that this explains 79% of the variability. So, if you are happy with this, then you can stop here. Instead of 5 variables, you just look at one single variable y1, and you have 80% of the almost 80% of the variability covered. Or else what you can do is that if you are not satisfied with this, along with y1 you can take the second column y2, and from that we see that it is a linear combination of the carbohydrates, the calories, and the vitamins, and this gives us the second variable. So, now y1 and y2 are the first 2 variables, and they together explain 99% of the variability. We need not go further, because it is almost the whole of the variability that has now been explained, and instead of x1, x2, x3, x4, x5, now we can work with only 2 variables y1 and y2 without losing too much of information, and these are the 2 formulas which gives us y1, y2 from the x's. Another example would be the height and weight example that we had looked before. The question was, do we need to look at both? We had data on 15 individuals, and we can find the principal components as before in this case also. So, the first principal component is y1, which is 0.595 into height, of course with the base changed, plus 0.803 of weight, and y2 is 0.803 of height minus 0.595 of weight. And if you want, you can discard the second variable, and you just look at the first variable, and that is the first principal component that we can have. So, as we saw, the red lines gave us the 2 principal components there. Now, are these combinations meaningful? If we take the log of what is referred to as the body mass index, all of you know what the body mass index is. Okay? It gives us an idea of how heavy a person is The doctors very often use this, and if you take the log of the BMI, it is basically log of weight minus twice log of height. If you make a log transformation of weight and height, this is the linear combination of weight and height. So, you can look at the log of BMI as a first principal component of heights and weights. Another such measure would be the body surface area as shown by Mosteller. He showed that log of BSA, the body surface area, is 0.5 log of weight plus 0.5 log of height minus log 60. So, again this is a linear combination of heights and weights in log, of course, and it gives us a single number, the body surface area, which can be used instead of quoting both the height and weight of the individuals. So, these are some of the meaningful combinations we can have. So, in this regard, I would just like to add that when you do a principal component, you have your x 1, x 2, x m variables, you get to y 1. It is important to interpret y 1 as, because it is a linear combination of the x's. Sometimes it is easy to do that, sometimes it may be difficult, because statistically you can just combine the variables, but it does not make a sense if you look at the practical aspect of it. When you look at the physical aspect, the combination of such variables may not be meaningful. Okay? So, you should be very careful when you use the principal component method. In today's lecture, we started with the different types of dimension reduction techniques, and subsequently we had been looking at the principal component method. We saw that the principal component method actually makes a linear combination of the variables and then chooses a few of these linear combinations which actually account for the maximum variability in the data. And then what we do is we take this principal components, as we call them, and discard the original variables, so that now we can deal with a fewer number of variables as compared to the initial number of variables. We saw a few examples of the principal component method, but in the subsequent lectures we will be looking at the results, that some of which we have stated in this module, and we will be looking at a broader aspect of how we can use principal components in other studies.